Hi everyone, in today's lesson we're going to talk about removing discontinuities. First, let's recall the three types of discontinuities. We can have a removable discontinuity or a hole, we can have an infinite discontinuity or a vertical asymptote, or we can have a jump discontinuity, which we likely see in piecewise functions. So let's take a look at an example. Example number 1 says, given the piecewise function f of x equals this, part 1, what is happening to the piecewise function at x equals 6? Is it continuous? Is there a hole, a jump, or a vertical asymptote? So the way that we can do this is actually by analyzing this piecewise function. So do you see here it says that we're going to use this function when x is not 6, and then we're going to use this function when x is 6. So because there's a singular value here, this just means a is a number, like 4 or 5 or 6. So this should tell you that down here we're saying, like say this is 4, if a is 4. So the y value, f of x, is 4 when x is 6. So what this is your function value, or your closed circle. So what that tells me is that we're pretty much going to use the top function everywhere else. So this actually tells me that there's a hole. So think of it, I'm just drawing a function and it could be wrong, like as far as what it looks like, but say that we have a curve, we have a hole, we have a curve, and then we have a function value. That's kind of what's happening here. So you have to be able to recognize that from the information that's given. So now it's saying for what values of a is f of x continuous at x equals 6? So in order to do that part, we actually have to use the limit definition of continuity. And that states that the limit as x approaches 6 in this case of f of x must equal f of 6, right? That's the definition of continuity, that the limit has to equal the function value. So before we can go ahead and plug into here and here, since we know that there's a hole, we actually have to remove the hole first, otherwise we won't be able to evaluate this limit. So in here, we could factor the top using am. So what numbers add to -3 that multiply to 18? And that's x minus 6 and x plus 3. And then on the bottom, we're leaving our x minus 6. So notice I'm going to remove my hole. By doing so, it'll allow me to plug into this limit. So now we want to take the limit and plug into this equation. The limit as x approaches 6 of f of x. So here is your function, but we're not using this function, the original, because if we did, 6 minus 6 would be 0, 6 minus 6 would be 0. We wouldn't be able to do that. So we're going to take the limit as x approaches 6 of our new simplified function, x plus 3, and we're going to try to set that equal to f of 6 to find our value for a. So to do this first limit over here, we're going to do direct substitution. So everywhere we see an x, we're going to put a 6. So 6 plus 3 is 9. And then over here, f of 6, we know that this is our function value, is simply a. So that means a is equal to 9. So what you solved for was the y value that we would, or excuse me, the a value that we would need to fill in this hole, right, up here. So pretend that this dot is no longer there and it's down in here. So now if a was equal to 9, we'd be able to fill in that hole, making this function continuous. Let's take a look at example number 2. So same situation, given the piecewise function here, what is happening? Well, this is very similar to what we did before. We have a rational function and then a value that we're going to use when x is 7. So this tells us again that this spot right here is our function value. So this is obviously going to be a hole, same scenario as before. And we can find the value for k to see if it's continuous at x equals 7 by using the formula for continuity. So the limit as x approaches 7 of f of x must equal the function value, so f of 7. So before we can take the limit of this f of x, we have to see if there are any holes. So I'm going to factor the top and the bottom. So I'm going to do this over here. So am for the top, what adds to -2 that multiplies to -8 is x minus 4 and x plus 2. And the bottom, what adds to -5 that multiplies to -14 is x minus 7 and x plus 2. So from what you can see here, the x plus 2's cancel, and we have x minus 4 over x minus 7. So when we evaluate the limit, we're going to use this simplified equation. So we're going to say the limit as x approaches 7 of f of x, which we'll use x minus 4 over x minus 7, must equal f of 7. And we know f of 7 is our function value, so at x equals 7, the value is k. And over here, we can just do direct substitution. Plug in 7 every time I see an x. So we can go ahead and do that. So 7 minus 4 over 7 minus 7. So what happens here is very interesting. Notice that 7 minus 7 is 0. So we have 3 over 0 equals k. So this is actually not possible because we're not allowed to divide by 0. So the conclusion that we can make here, when it asks for what value of k would f of x be continuous, you could say there are no values of k that would make f of x continuous. So a complete sentence, there are no values of k that would make f of x continuous. All right, let's move on to the back. Okay, so for the back problems, they're relatively the same. I took the liberty of putting the continuity definition up here for you, should you need it. Remember that the limit from the left has to equal the limit from the right, which has to equal the value of the function. Sometimes you can use the left and the right, and sometimes you can combine them and say the limit as x approaches c as a whole of f of x must equal f of c. And that's what we did in the front. We did that in the front page because there was no left and right. So basically, when there is a left and a right, you're going to use this one. And when there isn't, you're going to use this one. Now, most of the time, when there isn't a left and a right, you'll likely see that as a removable discontinuity. So just want to kind of give you that heads up. So let's take a look at one more example. We'll do example number 3. It says find the value of k that makes the function continuous and state the type of discontinuity. So if you notice, we have this function when x is greater than 5, so that's the right side. And then we have this function, 6x plus 6, when x is less than 5. That's from the left side. So it's clear that we have a left and a right side here, so we're going to use this first definition where you're going to use all 3 parts. So let's go ahead and write it out. We've got the limit as x approaches 5 of f of x, and that's from the left. We want to see if that's equal to the limit as x approaches 5 from the right of f of x, which equals f of 5. Now, I wasn't really specific in the directions as far as what value, so it just says find the value of k that makes the function continuous. I mean at the point where it joins. So same thing with this one, find the value of k that makes the function continuous. It joins at x equals -3. This one joins at 5, so that's the one we're going to use. So let's go ahead and finish this off now. We're going to take the limit as x approaches 5 from the left of this function, so we could write 6x plus 6. And then the limit as x approaches 5 from the right of the right side function, which is this one, so -8x plus k, equals f of 5. So now f of 5, we're looking for the function value, so we have to look for where the line is, so it's going to be in this one. So f of 5 means f of x, so x equals 5. So in this equation, we're going to put x to be 5, and we're going to leave k so that we can solve it. So -8 times 5 plus k. Okay, remember this piece, f of x, is where we substitute the 5 for, not the k. So here we're going to do direct substitution. So everywhere we see an x, we're going to put a 5. So 6 times 5 is 30, plus 6 is 36. Over here, we're going to do -8 times 5, which is -40. And then plus k. And then over here, -8 times 5 is -40, and then plus k. So what you'll notice when you're doing these problems, you're going to notice a little bit of overlap, right? Because the function value in these types of problems is found by using the right side. So I can't solve an equation with 3 parts, but I know that all 3 of them must be equal in order for it to be continuous. So I can disregard one of the 3 pieces and just set 2 of them equal to each other. So I'm going to choose to set these 2 equal to each other and solve from there. So we're going to do that over here. So we'll say 36 equals negative 40 plus k. And then we'll add 40 to both sides. And over here, k must equal 76. Now, what type of discontinuity do we have here? So we know that we have the removable when it was the problems like we did on the first page where we divided and canceled out the wholes. So our real only options here are vertical asymptotes and jumps. So vertical asymptotes really only come with rational functions or some of the trig functions. So in this particular case, the only thing left is going to be a jump. So if we want to state the type of discontinuity, we'll just write that it's a jump discontinuity. Okay, so it looks like here we have examples 4 and 5. I'd actually like you to try these on your own. 4 might be a little tricky. You might need to use some factoring for it. There might be more than one answer for k. That is a possibility. I know it says find the value of k, but it could be values of k. And try both of these, and we will start class off tomorrow that way. Okay, have a good night.